Okay, so we have one more example here of determining whether or not a given set is a basis for a particular vector space. This time we're looking at M22, all the 2 by 2 matrices. And notice this set contains these 3 2 by 2 matrices right here. Now, if you think about the standard basis for M22, which here's the general case, but it would contain 4 matrices, one for each entry that I could put a 1 in. It took 4 matrices to span all of M22 previously. One thing that we're going to show at the end of this section is that, well, a consequence, I guess I should say, of the last term we're going to show is that any basis for a particular vector space has to be of a unique size. Let me say that a little bit differently. If you take a look at all of the bases for any particular vector space, then they all have to have the same size. So in other words, if I've already found a basis for M22 that has 4 vectors in it, that would mean that any other basis for M22 would have to have exactly 4 vectors in it. It's impossible to have a basis with a different number of vectors. Now, we haven't proven that yet, so I can't use that result yet. But when we prove that result, we're going to show that if you have a set with too few vectors in it, then that's going to cost you your spanning. So in other words, there's no way for a set of this size to span M22. And then similarly, if a set has too many vectors in it, so more vectors than a basis for that vector space should have, we lose linear independence in that case. Again, haven't proven that yet, so I can't use those results. But thinking in that direction, I suspect that there's not enough vectors in this space, or in this set, to span all of M22. So I'm going to focus on the spanning condition here. And specifically what I want to do is construct a linear combination of these matrices, K1 times 1, 2, 0, 0, plus K2 times 2, 0, 1, 0, plus K3, squeeze that in there, zeros here, here, and here, and then 4 here. And I'm going to set that equal to a general 2 by 2 matrix, B1, B2, B3, B4. Okay, now notice what I could create a system of 4 equations out of this by multiplying my scalars in and then setting the sum of the first entries equal to B1 and then doing the same thing with the other 3 entries. So that's going to lead to the following system. K1 plus 2K2 equals B1. 2K1 plus 0 plus 0, so I'm not going to write those. B2, and then third entry, 0, K2 plus 0, so that's just going to be equals B3 here. Then I have a 0, another 0, and then a 4K3. 4K3 equals B4. So that's going to lead to a linear system that I want to attempt to solve. I'm going to do this one not in the form of a matrix equation like we did before, but in the form of an augmented matrix. So kind of the first way that we looked at solving linear systems. So that's going to look like this. I'm going to have 1, 2, 0, 1, 2, 0, B1. Okay? Then I'm going to have 2, 0, 0, B2. 0, 1, 0, B3. And then 0, 0, 4, B4. Okay? Now just again, one more time to remind you of the direction I'm trying to go here. I'm suspecting that this set is not a basis because it doesn't seem to have enough vectors in it compared to another basis that I've already found for M22. So if it doesn't span all of M22, then that should imply that this is not consistent for every vector B1 through B4 that I could choose here. In other words, this will not necessarily have a solution for every possible choice of these B's right here. but I need to show that somehow. Now notice I don't get to use my equivalence theorem here because the coefficient matrix is not square. It's a 4 by 3 matrix. So I have none of those tools available to me right now. Instead, what I want to do is approach this the way that we did back in section 1.6. Do just normal Gauss-Jordan elimination on it and see what comes out of that. Now, this one's not too difficult to do Gauss-Jordan on, and I'm going to skip the steps just because that's kind of old news at this point. But I am going to point something out once I get my reduced row echelon form here. 0, 1, 0, 0, 0, 1. Row of zeros down here. And then what I'll end up with here is a 1/2 B2, B3, 1/4 B4, and B1 minus 1/2 B2 minus 2 B3. Whoop. Okay. Got a little bit cramped there. Sorry about that. So, a couple of things. First of all, the approach that you might have seen me take here if I did show all of my steps, I noticed that the second through fourth row look like a diagonal matrix already if I ignore that first row. And the reduced row echelon form should also look like a diagonal matrix, but just with ones here. So what I did is I interchanged a bunch of rows until basically this 3 by 3 matrix was up here, and this last row came all the way down here. And then I multiplied by scalars, 1/2 here and 1/4 here, to turn this 2 and this 4 into ones. And then I added a couple of constant multiples of some of the rows to turn this last row into a row of zeros down here. But one important thing to notice about this augmented matrix is that when you're putting it in reduced row echelon form, you're guaranteed to get a row of zeros down here somewhere, right? At least one row of zeros, and that's what we're seeing right here. Why does that have to happen? Well, it's because I have more equations than I do unknowns for this system. Notice that because the coefficient matrix was a 4 by 3, that this diagonal with containing all the leading ones has to come to an end before it reaches the last row. And we know that if that happens, anything that comes after that, any rows after that, have to be rows of zeros if this is going to be reduced row echelon form. And it's exactly this row of zeros that's going to give us the proof that this set doesn't span all of M22. Remember, if this is going to be consistent, then this should be equal to 0. Remember, this is an equation that says 0 equals this expression right here. 0 equals B1 minus 1/2 B2 minus 2 B3. Okay? Because if this is equal to anything other than 0, then this would imply a contradiction, which gives us no solution. So, in other words, this system of equations this system of equations here is only ever consistent if this identity is, or if this equation holds. Notice this can be written this way as well. B1 equals 1/2 B2 plus 2 B3. Okay? Now that is why this set does not span all of M22, because if B1 is chosen in such a way that it's not equal to 1/2 B2 plus 2 B3, then that would mean that this system is inconsistent for that vector, which means we can't get that vector as a linear combination of the 3 that we were given in that set. Okay, so just to give you an example, let's remember where the B1 through B4 came from, and choose B1 and B2 and B3 intentionally so that this fails. So let's start with B2 and B3. Let's make them both 1s. This is kind of an arbitrary choice, but I'm just going to make them both 1s. Actually, let's make B2 a 2. Okay? Then if I were to plug those into this, B2 is 2, so that's 1/2 times 2, which is 1, plus 2 times 1, which is 2, so that becomes 3. If this system is going to be consistent, if this is going to work, then this first entry is going to have to be a 3. So I'm going to make it something else, maybe a 0. Notice B4 doesn't show up anywhere. It doesn't show up anywhere in this equation, so B4 can be anything that I want it to be, maybe 11, doesn't matter. So because this fails this requirement, then that's telling me that there is no linear combination of these 3 matrices up here that would ever give me this matrix. So I could say is not a linear combination of the given matrices so the set does not span M22, therefore not a basis. Okay, so we lose out on the spanning condition there. All right. So you've now seen a few different approaches to showing whether a vector space, or sorry, a given set is or is not a basis for a vector space. But now let's go into the reason we were even talking about bases in the first place. So at the beginning of the first video, I mentioned that the spanning condition guarantees that every vector in a vector space V can be represented as a linear combination of the vectors in our basis, and the linear independence condition guarantees that that representation is unique. And we're using that to come up with the concept of coordinates, something that you've been using since pre-algebra, using coordinate systems, the XY plane, for example. But we're generalizing that concept, and we're using the basis idea to do that. So this theorem here is summarizing what I just said. If S equals this set and it's a basis for some vector space V, then every vector in V can be expressed in exactly one way as a linear combination of those vectors. That's the purpose of a basis. That's why we talk about it. And again, this proof is not even really a proof. It just says it's clear from the stuff we've already talked about. Okay, so let's talk about coordinates now. Let's suppose we have a vector space V and we have some basis for that vector space, this V1 through Vn. Then let's choose some vector V in our vector space, lowercase v, and because this is a basis, that guarantees that we have a unique linear combination of these vectors that equals V. So I can write V as this linear combination C1 V1 plus C2 V2 and so on, where the set of scalars here being used for the C's are unique. There's only one set of C's that works for this. Okay, so those scalars in particular, C1 through Cn, are what we're going to call the coordinates of V, the vector V, relative to the basis S. And notice they depend on what these V's are. In a different basis, these scalars would have to be something different to give us that vector V. Hence the relative to S part of this. Okay, if we take those scalars and we put them in the form of an ordered n tuple, then we call that the coordinate vector of V relative to S. And we use this notation. We put parentheses around V with the S as a subscript, indicating which basis we're referring to when we talk about these coordinates. Okay, oftentimes it's useful to think of that vector as a column vector. Remember, by writing this as an ordered n tuple, what I'm doing is I'm taking the vector V, which comes from some general vector space V, and thinking of it as a vector in Rn. Rn is the space of all ordered n tuples of real numbers. Well, we showed that vectors in Rn can be written either in this form or in column vector form. So either of these are also acceptable for coordinate vectors. If I want to write my coordinate vector as a column vector like this, then I would use square brackets around the V instead of parentheses. Okay, so I want to practice finding coordinates or coordinate vectors for a particular vector from a vector space in different bases. Okay, and the couple of examples we're going to look at here is it's going to ask us to find the coordinate vectors relative to two different bases. So starting with this, we're in R2, and I want to find the coordinate vector of this, the vector 2, 3, relative to both the standard basis for R2 and the basis given here, 2, 0, 1, 1. Now notice I'm not asking you to prove that this is a basis. We're just going to take that for granted here. This is a basis, it turns out. All right, so to do this, let's start with the standard basis. Okay, remember the standard basis is ij. So what's the goal here? I want to write the vector 2, 3 as a linear combination of those standard basis vectors. But what we've already seen in the past is that this is equal to 2i plus 3j. It's very easy when we work with the standard basis, because the standard basis gives us coefficients that basically just match the exact coordinates that we already see there. So that means in the standard basis, my coordinate, let's call the standard basis in this case s, because I do need to give it some name, right? That would tell me that the coordinate vector for the vector v relative to s is, or no, I'm sorry, let me back that up. I already used s to describe this set. Let's call it s prime. Okay, so the coordinate vector in the standard basis, which I'm calling, the coordinate vector of v relative to the standard basis, which I'm calling s prime, is just the ordered pair containing these two scalars, 2, 3. Now that reveals something really, really important, which is when we're specifically working in Rn, the coordinate vector for any vector in Rn, not just R2, relative to the standard basis looks no different than the original vector. They're going to look identical. So it's very straightforward to come up with this. But let's look at our other basis. Okay, so s equals 2, 0, 1, 1. Calling that s. We're in s now, and we're still working with the vector 2, 3, but I need to figure out a different linear combination of these two vectors that comes out to this. Okay. Now there's a couple of different ways to come up with that linear combination, but I'm going to try to do this one by inspection. And one thing I notice, remember we're working with two vectors here, 2, 0, 1, 1. Notice that no matter what scalar I put in front of this vector, it's going to end up being multiplied to a 0 in the second component. So that's going to contribute nothing to the second component that we're getting here. This 3 is going to be determined entirely from this vector here. So that means that this has to be a 3. That's the only way I'm going to get a 3 in my second component. That makes sense? Now, with that in mind, that can help us determine this first scalar here. So notice if I multiply by 3, this will become a 3. But what do I really want? I want a 2. I don't want a 3. So I need to be able to subtract 1 from this 3 to get a 2. That means I should multiply this by something that puts a -1 here. Well, -1/2 would do it. Okay? And you can verify this would in fact add up to this vector right here. Now, the scalars in that linear combination are what become our coordinate vector relative to this basis s. So what I do is I can say my vector v, the coordinate vector for v relative to this different basis s, looks like -1/2, 3. Okay? Notice we're talking about the exact same vector here, but the way that I think of it in terms of its coordinates can be different, and it just depends on what I'm using as my basis. Okay? And there are very many applications in math where it's helpful to choose a different coordinate system than the standard one to solve a problem. We'll look at that later on down the road. So, you know, don't fall into the trap of thinking the normal standard basis that I'm used to is the only one I would ever need. Not the case. Okay? All right. Let's take a look at another example here. This time we're not working in some set of ordered n tuples. This is the vector space P2. So this time I want to find the coordinate vector for the polynomial p of x equals 4x squared minus 2x plus 1 relative to two different bases. My standard basis for P2 and this new basis here. And again, just because I'm showing you a set of vectors doesn't automatically mean it's a basis, but I'm claiming it's one here and I'm not asking you to prove it. So for the sake of this problem, we're just taking that for granted. Okay, if the set turned out to not be a basis at all, then we couldn't talk about coordinates. This would be a non-example. So taking for granted that this is a basis, let's take a look at the coordinates for starting with the standard basis, P2. Standard basis for P2. So let's call that S prime again. Standard basis P2. Now remember, the standard basis for P2 is the set of vectors 1, x, and x squared. And in this case, it's really straightforward. I'm going to write this in reverse order because if you notice, the vectors that I'm using for P2, I'm putting the constant term first and my quadratic term last. So how do I get 1 minus 2x plus 4x squared as a linear combination of the standard basis vectors? Well, it's right there in front of you. 1 times 1 plus negative 2 times x plus 4 times x squared. Here are the standard basis vectors for P2, and these scalars are the scalars that I would multiply each one by to produce this polynomial. It almost looks like I didn't even do anything. And that's because the standard basis is very easy to work in for this purpose. So how would I write my polynomial as a coordinate vector then? Well, my polynomial looks like p of x, but I want it to be written relative to the standard basis. And again, we're going to call that S prime. This time it's going to look like an ordered triple because there's 3 terms in this ordered pair. And so these guys, being my scalars, 1, negative 2, 4, those would be the the coordinates for this vector. Okay. Now notice really all I did, if you look at it carefully, it looks like it's just the coefficients. And that's the reason why the standard basis is easy to work with. The coordinates of this vector are just going to look like the coefficients of this polynomial. Now there's one thing I didn't point out previously, but I want to point it out now before moving on to the second part of this example. The order in a coordinate system matters, right? Notice if I had written this polynomial in the original order, 4x squared minus 2x plus 1, then my linear combination would have been written in a different order as well, giving me coordinates that are also in a different order, 4, negative 2, 1. That's what it would have looked like. But remember, ordered n-tuples, or in this case ordered triples, as the name implies, the order matters. 1, negative 2, 4 should be treated differently than 4, negative 2, 1. So how do we reconcile that with the idea of a basis? Because remember, the way that we think of a basis is as a set. Let's come back here for a second. This is the set of vectors that form the standard basis for Pn. We used these first 3 as our standard basis for P2. Sets, by definition, don't have any implied order. The set 1x, x squared is considered to be the same set as x squared, x1. But for the purpose of coordinates, we need some kind of prescribed order so that the coordinates make sense. And this gets us into something that we call an ordered basis. For the purpose of coordinates, we use an ordered basis. So basically that means that this is considered to be the order that I would write my linear combination in, giving me implied order for my coordinates. Okay, and that's the reason why I needed to rearrange these terms. So I'm seeing that I'm running out of time on this video. I'm going to do the other part of this example in the next one.